In this presentation, we're going to talk about the analysis of impurities in metals using the Avio 500 ICP-OES. In this talk, we're going to briefly highlight the features of the Avio 500 and get into spectral interferences and their management in the world of optical emission spectroscopy. In this case, we're going to talk about Interelement corrections, or IECs, or Multicomponent Spectral Fitting, MSF. Analysis of pure metals and alloys by ICP-OES requires some level of interference management, as these are usually looking for trace level of contaminant in metal concentrates. We're going to speak about some of those applications later on in the talk. PerkinElmer offers two models of ICP-OES. The Avio 200, which is on the left-hand side of this screen, is a sequential unit, whereas the Avio 500 is a true simultaneous ICP-OES and is equipped with two dedicated detectors. We're going to focus on the Avio 500 in this talk. The two Avio ICP-OES platforms are built using shared features. We're going to talk about the proprietary flat plate technology, the dual view optics, and PlasmaShear gas system. Firstly, let's talk about our flat plate technology. Flat plate technology replaced the aging technology of the load coil, delivering a matrix-tolerant plasma that runs most applications at a reduced argon flow rate. In addition to the huge advantage of argon savings, flat plate technology solved many of the challenges encountered with a traditional copper load coil. Our flat plate technology is made of a chemically resistant material, so it does not corrode and need replacing like a traditional coil. It's also self-cooling, reducing the risk for any leaks. Another feature that played a great role ensuring PerkinElmer ICP-OES are the preferred platform in the mining industry is the PlasmaShear gas. This is a patented technology that enables us to design a cone-free system where the PlasmaShear gas cuts off the tail plume of the plasma. This translates into cleaner windows, less maintenance, and more stability and reliability when running high levels of acids and total dissolved solids. Our PlasmaCam technology is a great feature for experienced users and those who handle troubleshooting. Being able to see the plasma with true color can tell us a lot about the plasma's health. We can know if there is an air leak, if there is plasma overloading, or if we have a deposition or blockage in the injector. It can also aid our service and application scientists with remote diagnostics. Next, we'll talk about our dual view technology. This gives us the best of both worlds. We're able to measure both minor and major elements in one run without any compromise. Its fully selectable radial viewing and axial sampling depths delivers the ultimate flexibility in optical emission analysis. The Avio 500 is a true simultaneous instrument with two dedicated detectors, one for the visible and one for the ultraviolet region. This is an optical design designed specifically for speed, accuracy, and precision. The Avio 500 is also equipped with universal data acquisition, a feature that enables this platform to acquire all 6,336 wavelengths and background points in the same analysis without any time penalty. This feature enables the user to perform all sorts of post-acquisition data analysis for ultimate flexibility in data analysis and interference corrections. So now let's talk about the ways that you can deal with interferences. Firstly, let's talk about inter-element corrections, or IECs. These are the measure of the effect of an interfering element upon the observed concentration of the analyte. It is the apparent concentration of the analyte in ppb which is the result of the interferent in ppm. The tables needed for IEC corrections are included in our Syngistics software. However, these tables can need updating for concentrations if the interference changes dramatically. Another way of dealing with spectral interferences is by using our Multicomponent Spectral Fitting, or MSF. MSF uses a multi-least square fit model. It's a robust method that uses the spectral information available and does not rely on setting any background points. It's very simple to use and is included in our Syngistics software. You build a model by selecting a blank, an interference, and an analyte spectra, and the software does the calculations for you. Now let's look at how MSF can be applied in the analysis of trace metals in steel. Now we're going to look at impurity analysis in steel using MSF. For this analysis, we created a simulated steel digest consisting of high amounts of iron, chromium, and nickel in a 16% aqua regia mix. We were looking for 7 analytes that are commonly found as impurities in steel, and our calibrations were also made in 16% aqua regia. The instrument conditions and setup for the Avio 500 can be seen in this slide, along with the wavelengths used for each of the elements that we wanted to measure for. When deciding whether you need to use an interference correction or not, you need to take a look at whether the peak is clearly resolved. In the case on this slide, we're looking at the lanthanum peak at 408. You can clearly see that this is resolved from the nickel and iron peaks on either side of it, so no correction is needed in this case. However, if we look at another example of zirconium and iron, you can see on the graph below that the zirconium peak is clearly overlapped by the iron peak. In the case of steel, iron is going to be very high, so zirconium is going to be a trace metal. Therefore, we're going to need to be able to resolve zirconium from iron. So let's look at how MSF can resolve zirconium from iron. In the graphs below, the blue lines are the spectra without MSF applied, and the pink lines are the spectra with MSF applied. On the left-hand side, you can just see the sample with and without MSF. With the MSF correction, you can see a good background with a very small bump where zirconium should be centered around. So now if we look at the right-hand side, where we've added 100 ppb of zirconium into the solution, you can clearly see that the zirconium peak. In this table, you can see the results for the 7 elements that were analysed for in this simulated still sample. You can see the sample concentration, the sample plus spike concentration, and the recovery. In this case, the spike was all at 100 ppb. The only element that used an MSF correction was zirconium, and you can see that spike recoveries were within 10% for all elements. So now let's look at impurity analysis in nickel and lead alloys. So nickel is one of the most widely used metals due to its corrosion resistance and strength at high and low temperatures. It's commonly used in steel and alloys, electronics, rechargeable batteries, and plating. Different grades or purities of nickel are required for different uses, and these are set out by the London Metal Exchange. Although lead is one of the most toxic metals and is being phased out for a wide variety of products and processes, it is still commonly used in a number of applications, such as lead-acid batteries, alloys, radiation shielding, flashing in the construction industry, ammunition, and lining in industrial pipes. Different grades and purities of lead, again, are required for different uses, and these are set out by the London Metal Exchange. For both of these analyses, we either used a 1% nickel or a 1% lead to simulate pure nickel or lead prepared at 100 times dilution. For the nickel calibrations, we used external calibrations in 5% nitric acid. However, for the lead calibrations, we used 1% PBB to overcome the matrix effects, which are not present when using nickel. For this, we used the method of standard additions and a sample intercept. The conditions in the Avio 500 can be seen on this slide. I'd like you to note the low argon flows of 8 litres per minute for the plasma gas flow, 0.2 litres per minute for the auxiliary gas flow, and 0.6 litres per minute for the nebulizer gas flow. On this slide, you can see the wavelengths used for the 10 elements that were analysed for in the lead matrix and the 12 elements that were analysed for in the nickel matrix. Scandium was used in internal standard for both matrices. I'd also like to point out that some of the wavelengths were not the same in each case, as for example arsenic, where the 188 line was used for nickel and the 193 line was used for lead. These wavelengths were chosen so that interference removals were not needed. Let's look at the nickel results. So we looked at spike recoveries in 1% nickel at ASTM levels of 99.8% nickel. As you can see, all the spike recoveries are within plus or minus 10%. Now let's look at the same for lead. In this case, spikes were added to simulate 99.97% or 99.985% lead. In the table on the left-hand side, you can see that this meant that, depending on the element, we had spikes of between 20 and 500 ppb. The graph on the right-hand side shows that all spike recoveries in these cases are between plus or minus 10%. On this slide, you can see the specifications for lead at 99.99% or 99.994%. You can see that with 100 times dilution, the lowest concentration that would need to be measured would be 20 ppb. So in this case, we added a 20 ppb spike and looked at the recoveries in 1% lead. And you can see that for all of these elements, we had a spike recovery of between plus or minus 10%. We also had to analyze the stability over time. So these are the results of the stability in 1% nickel analyzed for 6 hours looking at the internal standard of scandium. You can see there's a variation of less than plus or minus 5% over the whole 6 hours, showing good stability in these high matrix samples. We repeated for lead, where we looked at 1% lead and analyzed for 6 hours and again measured the internal standard of scandium. Again, you can see that the variation is less than plus or minus 5% for the entire 6 hours. The Avio 500 ICP-OES easily handles 1% lead or nickel solutions, allowing for accurate and stable analysis. In these examples, we looked at impurities in lead ranging from 99.97% to 99.994% purity, and the impurities in nickel at 99.8% purity. All of these were found to be very accurate within plus or minus 10%. The Avio 500 ICP-OES resolves challenging interferences in metallurgical samples with multi-component spectral fitting, or MSF. MSF allows analysis with normal resolution, enabling low levels to be measured, making it ideal for metallurgical samples. MSF is simple to use, robust, and is included with our Syngistics software for ICP-OES. Thank you for joining me for this presentation. Please feel free to ask any questions. Thank you.